Hello and welcome to a quick video where we will discuss floating point data types in Q. Firstly, what are floating point numbers? Floating point numbers are positive or negative numbers with an associated decimal or fractional component. Q has two floating point data types. This table summarizes the main characteristics of each of the floating point data types. The real data type represents an IEEE standard 4-byte single precision floating point number. This is often called a float in other traditional languages. The unique type number for a real is 8 and its unique type character is the letter E. We can represent the real value 17.5 by writing 17.5e. Null and infinity can be represented with a 0ne and a 0we respectively. Notice that the n and w can either be lower or uppercase. Real values range from approximately minus 3.403 times 10 to the 38 to 3.403 times 10 to the 38, and a real can hold at least 6 decimal digits of precision. The float data type represents an IEEE standard 8-byte double precision floating point number. This is often called a double in traditional languages. The unique type number for a float is 9, and its unique type character is the letter F. We can represent the float value 17.5 by writing 17.5f or just 17.5 since a float is the default floating point type in Q. Null and infinity can be represented with a 0nf and a 0wf respectively. Notice that the n and w can either be lower or uppercase. However, because floats are the default floating point type, we can omit the trailing f and use 0 lowercase n and 0 lowercase w to represent the float null and infinity values respectively. Note that in this case, if we leave out the trailing f, then we have to use a lowercase n or lowercase w. Floats range from approximately minus 1.798 times 10 to the 308 to 1.798 times 10 to the 308. A float can hold at least 15 decimal digits of precision. As mentioned in the previous slide, the float is the default floating point type in Q. Floating point numbers will only be a real type if the E character suffix is appended to the number. For example, 7.5e is the real value 7.5, whereas 7.5f and 7.5 both define the float value 7.5. Let's now discuss the behaviors of infinity and null with respect to floating point values. Arithmetic on real and floating point infinity values behave as expected, rather than wrapping like integer types. So 10 plus the real infinity value just gives the real infinity value. And 10 plus the float infinity value gives the float infinity value, i.e. adding any number to infinity will result in infinity. Division of a positive or negative numeric value by 0 results in the positive or negative infinity float. For example, 123 divided by 0 yields infinity, and minus 123 divided by 0 yields minus infinity. Division of 0 by 0 is undefined in mathematics and thus results in a null float in Q. So 0 divided by 0 gives 0n. A floating point value can also be described using scientific notation. For example, 1.234e05, 1.234e plus 5, and 1.234e5 all equal the float value 123,400. 1.234e minus 3 equals the float value 0.0012340000000000001. This last example shows how many floating point numbers are merely approximations to the actual real decimal numbers that they represent due to the finiteness of computer memory. The E stands for exponent, i.e. a power of 10. To the right of the E is a signed exponent. Note that the 0 and plus are optional. Scientific notation of reals is awkward, given the presence of E both for the exponent and the type indicator. For example, 1.234e3e is the real value 1.234e3. The Q console display defaults to 7 decimal digits of accuracy for float and real values by rounding the display in the 7th significant digit, even though more digits are actually stored in Q. We can use the \P system command to check and change the display. For example, \P on its own will tell us the current display value, \P2 will show up to 2 decimal digits of accuracy, and \P0 will show up to the max decimal digits of accuracy, which is 17 decimal digits. When comparing floating point numbers in Q, Q will perform a tolerance check. For example, if we take the sum of 7 sevenths, we do not get exactly 1 due to floating point precision, but we can compare the result with 1 to see if it is tolerantly equal, greater than, or less than. The only exception to this is comparing with 0. Only 0 is tolerantly the same as 0. So even for a really small value like 1 times 10 to the power of minus 300, 0 is not tolerantly equal. Therefore, intolerant comparisons can be checked using 0 equals x minus y. To give a formal definition of comparison tolerance, we say that there is a comparison tolerance T such that if x or y is a finite floating point number, then x equals y is true if magnitude of the difference of x and y is not more than t times the maximum magnitude of x and y. In Q, t equals 2 to the power of minus 43, and this value cannot be changed. Comparison tolerance is built into the equals, less than, greater than, less than or equal to, greater than or equal to, and the match operators. It is also built into the differ and within keywords, and also the converge, while, and do iterators. We look at some other interesting properties of floating point types and comparison tolerance. Comparison tolerance is not transitive. For example, if we assign A, B, and C as shown, and then check if A is equal to B, we get true. If we check if B is equal to C, we get true. But when we check if A is equal to C, we get false. So just because A is tolerantly equal to B and B is tolerantly equal to C does not necessarily mean that A will be tolerantly equal to C. Another property is that floating point addition is not associative. For example, if we sum over a large list of small floating point numbers and then reverse the list and sum, we get 2 different results. So that's everything for the floating point data type in Q. Thanks for watching, and I will see you in the next one.